we have visitors that come from a long, long way away to come and visit us. And tonight we've got Clay Koplin and his friends who've come from Alaska. And I first met Clay in Reykjavik at something called the Arctic Assembly. And that's an event that Orkney's been engaging with for the last 3 or 4 years. Really, obviously, we have that tremendous Arctic heritage in our history, and I think there's an interesting opportunity for us to, if you like, reacquaint ourselves politically with that part of the world and be a part of what's happening. So this talk reflects both the energy side, but also maybe that Arctic side as well. So I thought we were ready to go, but is that one of your slides? That is one of your slides, yes. Yeah. So we are ready. So what I'll do is get Clay to come up and talk to us, and he's got about half an hour or ish of presentation, and then obviously he's very happy to take questions, and I think things he's going to talk about will be quite discussive things, so we can get into the guts of it afterwards. So enjoy it. Clay, take the floor.
Okay, thank you, Gareth, and I want to thank Gareth and Inga Burton for setting this up and allowing us to speak. It's my wife and my second trip here to Orkney, and we love it. It has a lot of similarities to our community. And so I'll just introduce the community of Cordova a little bit. It's what we call a remote microgrid. So it's not connected by the road system to the rest of Alaska. So much like Orkney, we do have daily jet service, which is fantastic, by Alaska Airlines, but otherwise you have to take a ferry in and out of the community. And we're not connected electrically to any other communities. We have no transmission lines. The distances are just too far. However, we do have an amazing resource of hydropower. Cordova is in south central Alaska, so as you look at the panhandle of Alaska, Cordova is right where the handle meets the pan, and we're the last community up coast in the coastal rainforest. So we average about 5 meters of precipitation annually. So water's our resource, and you can see from the steep terrain that we've developed hydroelectric projects. That and converting to underground power lines is what originally attracted me to Cordova. Building a new renewable energy project, and I'm a big fan of underground and submarine cables. I know it's not unusual in Scotland or in Europe, but it's quite unusual in the United States to have underground power lines. I think I can fill in some gaps on Cordova through these other slides, but I will say that when we invested in renewable energy, and now we're knocking on the door of 80% renewable year-round, but in the summer, when we have all of our seafood processing, we're pretty much 100% hydropower. We produce hydro for under 8 cents a kilowatt hour. Diesel is about 50 cents a kilowatt hour right now. And so that lower cost and stably priced energy allowed our seafood industry to start bringing all the seafood onshore to process it in the community instead of on floating ships. And we get a tax from that, the raw fish tax it's called in Alaska. So that's really ushered in a lot of prosperity in our community. And now this little town of community of 2,600 people, we average about $100 million annual seafood economy. So we rank about the 11th largest in the United States, and we've really built that on a renewable energy platform. So we're a very small organization, so we have to, what I say, we partner fiercely. So we know where we're going and the steps that we have to take to get there to get completely off of diesel, but we don't have a lot of resources. Much of that $100 million economy actually resides with the seafood processors, the fishermen who come in and then leave. Not a lot of it stays in the community, so we have limited resources to work with. So we work a lot with our state and federal governments, our tribal organizations, the city of Cordova, others in the communities. Coastal Alaska is a very harsh environment. It's not unusual for us to get nearly 2 meters of wet snow in one day. We have winds exceeding 150 miles an hour. We had a couple of the events in this picture. We got 48 inches, so about 1.5 meters of rain in 3 days, and it happened twice in one summer. So these are just pictures of some of the challenges we've faced, and it's hard to really appreciate the scale of this river, but the average flow in that river is about 100 cubic feet per second. That right there is about 5,000 cubic feet per second. So about a 1 in 3,000 year event, supposedly. But we're seeing these large events more frequently and more severe. An avalanche hit our, you'll see another picture of our Run of the River Hydro project. We have an inflatable rubber dam that's about 3 meters in diameter and 20 meters wide. We just inflate that and it creates a pond that the water can flow into the pipeline and down to the hydro plant. Well, it got hit by an avalanche, came down the mountain and turned upstream and tore it up, and it was a really dangerous thing to get it fixed. But lots of dynamics that we have to manage, so we're constantly adapting our equipment and our plants to manage this this climate. So we have to innovate. It's one of our levers to get the highest and best value out of our electric grid and for our community. We are looking for technologies that haven't been developed yet. We are moving towards a very smart grid, smart city platform where we have a real interactive system where, for example, instead of spilling excess hydropower from our electric plants, we could start charging electric vehicles or using air source heat pumps to heat homes, which is much more efficient than just direct electric heating. So as we have advanced our technology and our grid, the Department of Energy and others started recognizing that we had taken the state of technology just on our remote grid up to where the national labs and others were. So that really attracted more of their partnership, and we ended up hosting the largest grid modernization project in the U.S. here in our community, and are making some breakthroughs for our Department of Energy. That's what this little slide here, tightly coupled microgrids. So we've actually have developed somewhat of a self-healing element to our grid, so that if there's a large storm coming or a tsunami, there are ways that we can reconfigure our grid just before and during and after an event like that to make sure that we especially keep our critical loads in power, our hospitals, our water treatment plants, and so forth. We've installed free electric vehicle charging stations at our community center above and below, and we're looking forward to electrified planes, ferries, and again, with our abundant hydropower, we can use locally sourced energy to have a more stable and a self-sufficiency. We don't rely on having to ship diesel into the community. More and more on the world stage, you can't be sure from one year to the next if fuel can even arrive in your community. Some of the socio-political events of the world. But so there's a lot of innovation in our community outside energy. We had our seafood industry in Cordova really moved Alaska's salmon processing in particular towards a quality market. So instead of just the high volume, low value markets where you just harvest huge amounts to overcome the shipping costs, they started really innovating in that area as well. First, icing the salmon, years later, live bleeding the salmon to improve the quality, and now even pressure bleeding, where they can put a small needle in the spine, pressure bleed them, and they can stay shelf stable for up to 2 weeks. And so some of our fishermen, small boat builders, have gotten patents around some of these technologies. This young gentleman in the background, he went to Oregon State University. He'd grown up working in Cordova, but he went to Oregon State. He decided in his 30s he wanted to get his mechanical engineering degree. And he saw the wave energy test system there in Oregon and got excited about it. So he and his partner self-designed a wave energy generator. And their father-in-law in Cordova machined all the parts for him. They built it in their garage just out of pocket. Well, it cost $50,000 a week to use that wave energy test center. So they had kind of scrapped the idea, but then the U.S. Department of Energy had what they call a Wave X prize, that anybody could enter the competition, and if they could at least get twice the kilowatt-hour output per unit cost for building the device, then they were eligible to win the prize. Well, long story short, they beat out 96 other teams that had been working on their technologies for quite some time. They won the X Prize, and now they're building scale versions for the U.S. Navy, but born and raised in Cordova. So a lot of ingenuity out of a small town. I wanted to talk a little bit about, I'm very passionate about underground power lines and submarine cables because in our harsh climate, it's a way to keep the lights on. If you get it underground, out of sight and out of mind, there's all kinds of value streams that come from that. The visual aesthetics, the high reliability, not having trees tear down your lines. And then there's actually some technical advantages. But safety is another advantage of underground power lines. The cable's already in the ground, it's very difficult to get electrocuted. So the life safety aspect's quite nice. But we've had to, and me particularly at Kodiak Electric as their staff engineer, and then in Cordova where they had set a policy to convert everything to underground. By the time I got to Cordova, most of that had been completed. And what was left was all the stuff. The 20 to 25% of overhead that still had to be converted was in places where there was solid rock or a rock wall, a paved street, and then straight into the ocean. And so to find corridors and places to put that, or to cross steep canyons or bridges, had to come up with a solution to every problem, which is challenging but fun, but then you kind of build a portfolio of tricks. And I'll talk a little bit about underground as I explain how our hydro system works. But we had a submarine cable fault, and my understanding is that there's a submarine cable built at Orkney that failed recently. So we had a submarine cable going to one of our hydroelectric plants, and a couple of engineers in Alaska had developed a very simple way to find faults in what you call a high impedance fault. So if you think of a big water line that has a tiny pinhole in it, it's very hard to locate that fault. Most of the time when submarine or electric power cables fail, it's a solid failure like a burst pipeline. Very easy to tell where the pressure is. But if you have a little tiny pinhole and you're leaking a little water out of it, it's very hard to detect that. So you call that a high impedance fault where there's just a little bit of current that's able to go to ground. And that's the problem that we had in our cable. Well, it turns out that these two electrical engineers had realized it really doesn't matter what voltage you energize a cable to or how long the cable is. It still follows Ohm's law that the current flowing through the cable times the resistance is the voltage. So we energized it with a 12-volt battery, a 4-mile long submarine cable, and then just use a simple voltage divider out to 4 decimal points, so very accurate measurements of the voltage between those lines. And we were able to find the fault within 10 feet. And then we were able to schedule the right tides and daylight and everything to dive on the cable, cut it in half, bring it to the surface. So this is a technology that might or might not work to find that cable fault. I know in Anchorage, they had a 138,000 volt line over to the natural gas plant that provides most of Anchorage's power, and they couldn't find the faults. They spent $3 million cutting the line and resplicing it, trying to get closer to where the fault was. And these two engineers used the car battery, and they found that the fault was 400 feet away and below the low tide line. So they were actually able to drive down and dig it up and fix it. And I think they charged Chugach Electric $2,200 to find the problem. So I used some tools to do that, some brand new that I purchased. One was 70 years old. I had no information on where the cable was or how deep it was, but it turns out that this orange device on the left is just a 60 hertz. It can tell where there's 60 hertz signal in the ground, but I found that by using this fault wizard and putting a 1,000 volt pulse on the cable, I could use this little MetroTel, this orange unit, and hold it in the water. And even in 90 feet of water, I could hear that clicking, and I could stay within 10 feet of it on the surface. If you get farther away, it would get quieter and quieter. So I just kept it as loud as I could, was able to find the cable and eventually drill on where the fault was. So in the background, it's a simple thing, but we always try to use local knowledge and local ingenuity because often that's all you have available. We don't necessarily want to have to wait 2 months for someone to show up in Seattle, charge us $150,000 just to come there, and then $5,000 a day for divers to just start looking for the problem. And if we can solve it ourselves. So anyway, we get on the table on these steel reels, and normally it would just be the 2 reels outside with 1 roll of wire. But to be able to use this local fishing boat, we disassembled those and reassembled them with 4 bays of wire, because there's actually 4 wires going out to the project site, and we the spliced out that had failed, and then we lifted them to the surface and spliced a piece in and dropped them back in. So just simple things like that, making a little reel that can fit on your boat deck. There's always dozens of little obstacles to get something done, and you just have to adapt and overcome. Just taking the boom of the boat, hanging blue tarps to create a tent that you can work out of. Apologies there.
It's not just
I have my ringer on. Please turn your ringers off for courtesy. But it just gives us a dry place to make the highest quality splices we can. This cable's been in service for 35 years and we want it to stay that way. And by the way, this is standard underground cable. We can install this for about 1/10 of the cost of the steel armored cable, and we can fix it for maybe 100th of the cost. So it's a completely different approach. We don't try to bulletproof our submarine cable, because even the armored cables will fail. But when they fail, it's very expensive. You're talking about millions of dollars to repair them. So at least in a shallow inshore environment that I'm most familiar with, down to 200 or 300 feet of depth, we just use standard underground cables. Now I've had them add some features, like put a thicker outer jacket. We use a very tough splice that has a series of 4 heat shrinks and kind of armored exterior. But again, it's a fraction of the cost, and if it fails, it's easily repaired. So a little bit about resilience. I'm still feel like Cordova is a bit of a case study for me, and I'm fascinated by what makes the community tick, because it seems like time and again they get knocked flat by a major disaster, and they bounce back and reinvent themselves to something often even greater. So starting with the native tribes that were there, and the disease and war that decimated their very successful culture around the local raw copper and tools and trade that they had. They discovered the richest copper mine, copper vein, about 200 miles from Cordova. They built the Copper River Northwest Railroad. It was the largest private railroad in the world at the time, 220 miles through wetlands, basically, up to the copper. So until 1938, they were hauling pretty much copper out of the ground. It was very rich ore. But when that mine played out, the railroad closed shop. They hauled all their cars away, picked up the steel tracks, shipped everything out, and just overnight it was just economically devastated. So they started razor clamming. It became a huge clam industry. They had 13 clam canneries and were called the razor clam capital of the world. But then we had what they called the Great Alaska Earthquake in 1964, the second largest recorded earthquake in history. And that was epicenter just 50 miles away in the middle of Prince William Sound. And in our region, some of the large islands that were Montagues, maybe 30 or 40 miles long, it tipped, it would drop 25 feet on one side and raise 35 feet on the other. In this whole region around the community of Cordova, it uplifted 8 to 10 feet, and just overnight the clam beds were destroyed. So the salmon fisheries were struggling. They would have some good runs and bad. So the volunteers went out and built a lot of, see how we're doing on time here, went out and built a lot of hatcheries, and they started building that quality model around the Copper River salmon. So that salmon here in a couple weeks is going to be retailing for 100 to 200 pounds sterling per kilo. So they really built a quality brand around that. In 1989, we had the Exxon Valdez oil spill in Prince William Sound that really devastated our fisheries. And so they took after the oil spill, they applied that quality model to our hatchery fish, the pink salmon, which were kind of considered lower quality and a much higher volume. But they were able to elevate the price from like 7 cents a pound to 30, 50 cents a pound to the fishermen. And it's created a juggernaut. That's what's elevated us from 26th largest seafood port to 11th. But each time Cordova, when faced with adversity, they would look at the resources they had around them and figure out a way to apply those to a new business model. I won't get into too much detail with Power Creek, just to explain how we use our battery energy storage system, because it's a really great use case. So the good news about this is that whenever there's water spilling over the dam, it means we're 100% hydro, because we're powering the entire community with that. This hydro plant has about a 3-meter diameter pipeline, a huge pipeline that's 1.5 miles long. And to respond to the rapid changes in our electric system, it has to be able to fluctuate the amount of power that's delivering. This is a little of daily loads on our electric system. So this red line is the average use year of our electric grid. Each of these blue plots is the daily load on the system for the 24 hours. You'll see in the winter here, it's very consistent. Comes up in the morning, at night. But you'll see as we get into summer in June, July, and August, it gets very dynamic. Our fish show up, lots of electric loads start to the grid. They're dropped on and off as big freezer compressor processing seafood. This is the bucking bronco that we have to somehow manage with our electric grid. Our generators and equipment has to respond to all this craziness. And we can jump from 3 megawatts to 9 megawatts in 30 minutes and back. So the only way that we could do that is to the jets of water hitting our turbine, so the turbine blades, we had deflectors. So a jet of water is hitting the turbine, we have deflectors that we would control very precisely. And if extra load was added, we could pull the deflectors out a little bit and instantly deliver more horsepower. So that allowed us to be 100% hydro. The problem was we had to waste a lot of our renewable energy capacity to do that. And then as we ran short, we would have to start diesels while we're spilling renewable energy. So to govern our system dynamics, that's why we bought the battery energy storage system. So we pull the deflectors out, we can deliver all the hydro that's available. As a big load is added to our microgrid, the battery just discharges power. And while it's discharging, the slower moving valves can open up on the hydro until the hydro is rebalanced and is carrying all the load again. And then if a big electric load is turned off, the battery can charge from the extra power from the hydro. So that's allowed us to save 50 to 60,000 gallons of diesel a year just by replacing that load balancing and frequency control. It's taking thousands of hours off of our diesels, which are very expensive to operate and maintain. And that's basically the use case for our battery energy storage system. One little trick that we learned from our electric power lines, I really don't know of anyone else in the world that's doing this, but underground power lines develop an electric field that you have to provide energy to just to build the electric field so that power can actually start flowing through the cable. And that, let's just say that pulls the power factor in one direction. Well, motors and generators and whatnot, anything with a coil of wire, it has to build a magnetic field before it can start delivering horsepower and turning. So it uses energy, builds that field up before it can start transferring the power, and it pulls the power factor in the other direction. Well, it turns out with all of our seafood processing loads in the summer, as we convert it to underground power lines, those electric fields cancel the magnetic fields so that basically our system operates at pretty much perfect efficiency. We can deliver 100% real power, horsepower through our lines because they're kind of balanced in a unique way. So that's allowed us to run our 6 megawatt hydro plant up close to 7 megawatts and save a tremendous amount of diesel fuel and leverage our underground power lines in a unique way to get more power out of it. So this is just a little look at our hydro plant again to show the good news is that we're 100% hydro in a picture like that. The bad news is we're paying $6 a gallon for gasoline. We're paying $5 a gallon for fuel oil to heat our homes, and we're wasting probably 2 megawatts of excess electricity here that we could be using to charge electric vehicles. So that's the opportunity that we're moving towards with our controls and our dispatching and we have a very highly automated power delivery system on our side. We run our plants unmanned, and they just call us out if there's an alarm or a problem. We can pull up cameras to look at what's going on. Even when the gravel accumulates in this, we have sensors that let us know that. It'll automatically transfer the load to the diesels, deflate the dam, flush all the gravel out, reinflate the dam, put the power back on the hydro, all in about 30 minutes time while we're all sleeping at 2 or 3 in the morning. So we have a very advanced system on our side but on the customer side, we don't have the controls, the communications we need to have that interactive handshaking grid. So we learned a lot of lessons about our battery energy storage system the hard way. We very often have to really push on vendors to have them, you know, when you're relying on a battery energy storage system to balance your system frequency, if you have the slightest communications failure or one component fails, that's a power outage. And for our seafood processors, we'll go 7 or 8 years without a single outage during the entire seafood processing season. So we're extremely sensitive to our high reliability, and we want assets like this to improve the reliability, not degrade them. So we have to do quite a bit of arm wrestling and get them to change some of their communications algorithms to be what we would call, you know, industry standard. I say microgrids are performance space. It's like a NASCAR, it's like a racetrack. It's not like driving back and forth to work every day. Everything has to work. It has to work all the time, or it's an outage or a problem. So as we look to the future, this is a little lake that's behind our community. That area at the bottom of the screen is the northern edge of our town. We are running short on water in the summer because our seafood industry is using a lot. We're having, again, these weather extremes where we're having droughts sometimes in the summer. So there's a little catchment at the bottom of the hill here at 200 feet of elevation, but that supplies about a third of the community's water, but they don't have any control over how much and when that water is available. What we're looking at doing is building a small dam up in that hanging lake. It's all solid rock. There's a little outflow. A little 20-foot tall dam could triple the storage there. Then we can release the water when we need it, and we can generate renewable energy with it. This is 1,500 feet of elevation. So one of the kind of unique things we want to do with it is you can see this watershed up here all collects right here at that little notch. That's 900 feet of elevation. So if we had a small catchment here and could pump water up into this lake, all of this water could be added to the system for renewable energy and water supply. But the other thing is the power plant would be at the bottom of the mountain. So let's just say 600 horsepower to get the water from 900 feet of elevation to 1,500, but then it's 1,400 feet of drop down to the ocean. So when you pump water into that lake, it actually takes a lot less energy to pump it up than you get out of it through your hydro plant. So it's almost like a perpetual motion machine. So with the rest of our grid spilling a lot of excess energy, now instead of spilling excess energy, you can be running your pumps to add stored energy and converting that temporary energy into stored energy that can take you through the winter. That's where we use most of our diesel. And then hydros are real conducive to manual controls. You can still open valves, have an old flyball governor, and close in a sync scope. And if every electronic device in your system has failed, you can still, what we call cyber black start your project and keep your lights and water supply on for your community. And in fact, the high volume pumps and pipelines into town could easily quick fill a barge. So if we have another earthquake or a real disaster, we can be an emergency water supply for the region. So I'll take a breath there and gladly field any questions or just open up a general discussion.
Well, there's a tremendous amount of innovation there in a very, very small place. 2,600 people, I think you were saying, at Lake Stromness, you know, and yeah, some amazing things. So I know some of you might have technical questions, some of you might have other kinds of questions. Does anybody have one they'd like to start with?
Yeah, quick one. Your inflatable dam.
Yeah.
So what's the longevity of that before you need to replace it, or are there major repairs? How does it cope with that use, that environment?
It's a good question. Before we used that technology, I went on a tour of northwestern United States and looked at some of those dams. I saw some that had been in service for 30 or 40 years, and they had bullet holes in them that they just put a patch on. It's very low pressure, and they were in the direct bright sunlight, whereas ours is mostly in the shade and cloud cover. We should have got 50 years of service out of that bladder, but because of the extreme flooding that I showed in that one picture, there were boulders the size of cars rolling down the river, and it tore that dam in several places. And we found that we were able to patch them and everything, but they said that everyone we talked to, the manufacturer and competitors, said that when those dams fail, they fail in one big rip all at once, and there's no fixing it. So that hydroelectric project saves over 1 million gallons of diesel fuel a year, and to lose that project easily doubles our cost of power, triples it in the summer. So we had to replace that after 18 years. I'm in the process of designing a diversion trench around that project that we can pass larger flows, and it'll also allow us to change it out next time. Unfortunately, when the flows are high, we can't get into the river to do the work. But then if you wait till winter, you're right at the base of severe avalanche, just like that avalanche that took the other one out. So that was the most uncomfortable thing I've ever done in my career, is having people working under those extreme avalanche risks to replace that. $1 million to replace that $250,000 bladder. So it's a good question. I hope to get 40 or 50 years of service out of the one that we have now.
Yeah, hi, that was great, fascinating. Really nice to meet you. My name's Scott. I work for a company called 360 Energy Renewables. We're recently on the island through an acquisition of a small business up here. So this is all kind of new to me. But you were talking about the submerged cables.
Yeah.
Failure.
Yeah.
Cheaper, obviously, to pull up, to redress. What is the frequency of failure for that type of cable versus your typical kind of armoured cable? Are you seeing, do these things on a general use case see similar failure rates, or are you repairing more?
I think they can have similar failure rates but it all depends on, with either armored cables or with standard underground cables, the location, the siting and location of it is what's really critical. You want to put it where it's not exposed to natural phenomena and disasters, and you also want to keep it out of the way of boat traffic and anchorages and fishing communities. So there's a little island off the coast of Maine that's one of the most busily trafficked stretches of coast. They have a submarine cable, just a stock standard underground cable that's been there for over 30 years without a failure. And I said, how does that even happen with all of the fishing and everything going on? But they had local lobstermen pick the routing for it so that it was on good flat bottom where it wouldn't rub and wear the cable, and where it wouldn't be impacted by the fishing fleet. So I think the reliability can be a lot similar between them, but the cost, there's such a huge cost differential, and it's so quick to repair the kind of the lower end cable when it does fail, particularly in island environments. I think it's we're just working with the Federal Aviation Administration to extend our grid 27 miles out to a very small remote diesel aviation supply site that provides all the air support from Seattle and Anchorage, Anchorage is the 5th largest freight air freight port in the United States. So it's a real critical site, but I'm working with them to use exactly that, just a lower cost way to get them tied to our grid.
It's fascinating because we're just about in. Also, most of us know there's offshore wind coming here, and a lot of those cables are probably going to be at water depths and in conditions that actually are not particularly abrasive.
Yeah.
But I bet most of them are going for armoured cabling because somebody will be trying to, well, A, make money out of it, and B, they won't be prepared to take the risk. And I just think there's a huge lesson.
Absolutely.
There.
And there's not enough cable. So again, supply chain can't cope. You need the amount you're going to need to build out this infrastructure ultimately that's going to power a lot of things in the future. It's really interesting.
Yeah.
Really interesting.
Yeah, we're just pushing a few megawatts around, but at 35 kilovolts even, 15 or 20 megawatts.
These are 20 megawatt turbines that are going to be connected. So it's
that's about right. 35 kV, like a 1-aught or a 4-aught cable would be plenty. So
Interesting.
any other?
How will winter temperatures affect the hydro system?
Good question. It's there's a lot of things that happen out in the natural environment that are really counterintuitive. Our river water actually gets coldest in the spring because of snow and glacier melt takes it right down to the freezing point. In the winter, as we get snow cover on the ground, the water water temperature actually warms up and it gets closer to 40 Fahrenheit, be more like 4 or 5 degrees Celsius. So it actually gets a bit warmer in the summer. You'll see the steam boiling off, but it's much like a conventional dam. It'll freeze over on top. Sometimes you'll even get 2 or 3 feet of snow, but the water is still flowing underneath the ice. And we, even in the worst, lowest flows in the winter, we'll still get 200 or 300 kilowatts out of the project, which is 20 gallons of diesel. Doesn't sound like much, but you add it up over a day and a week and a month, it's significant. So.
Martin?
Does your high voltage system have a neutral? You've got 4 wires, you don't normally only have 3 in a HV system.
We normally don't have what?
Well, you said you were running 4 wires.
Yeah. Oh, I'm
Does it
sorry.
have a neutral then?
One was a spare. So each wire has a neutral wrapped around it, and then they're connected at both ends. But they ran a 4th cable just as a spare, and it actually failed right after they installed it. And you know, so
it's a conventional 3-wire high voltage system.
it's traditional 3-wire. Yeah.
I mean, I've seen 4-wire high voltage systems in some places.
Interesting.
In Iceland, for one.
Yeah.
But it is right. Okay, there's a spare wire. That's why you've got 4.
Exactly.
Another question I was going to ask. You showed all the variations in load during the day.
Yeah.
Have you got any variable frequency loads which will allow you to switch on the load when the frequency rises and to switch the load off when the frequency drops?
That's a
How
good.
do you better manage that?
Good question. And I think you've done some of that in Orkney that I was very interested in, maybe managed loads and dispatchable loads. Have you done some of that? Or?
Well, there has been some, but it hasn't been frequency responsive because the frequency in Orkney is tied to the GB's national frequency. But in your case, I can point out where there is a frequency responsive load, and that's in Fair Isle.
Yeah, okay, in Faroes?
Fair Isle.
Fair Isle.
Between
okay.
Shetland.
Okay, gotcha.
It's a small network. It's about 100 people supplying on it.
We aren't yet. So we do have an electric boiler. So we're always trying to optimize all of our equipment. And we recently upgraded our diesel plant to connect them all into one heat loop. And then it turns out that when you have the diesel plant turned off, you still have to keep them warm and ready to run very quickly. And so we were running a diesel boiler and burning 25,000 gallons of diesel a year, just keeping our diesels warm and ready to run. And we're spilling hydropower for most of that. So we installed a electric boiler, and it has a bunch of steps in it so that we can step those up and down. It's not responding to frequency. Many Alaskan off-grid communities are using electric boiler for their frequency response, and they'll overbuild their wind and solar. And instead of just wasting that, they will dispatch it as heat to a community's facility, and they're also using it for frequency response. So they'll stabilize their grid with an electric boiler. We aren't doing that in Cordova, but so on the other side of that, when we lose a generator and we don't have enough generation, we just have the old traditional load shedding scheme where we open our least important circuit, and if frequency continues to drop, we open another circuit, and we shed as much load as we can to keep the other customers on, so we don't have a system-wide outage. But what we started working on with the Department of Energy, I'll keep it short, I guess. We can turn each meter off. We just deployed advanced metering, so we can turn each meter in our system on or off remotely. And I realized, wait a second, if we need to shed load, we don't have to do it a whole circuit at a time. We can just shed residential loads, for example, and just shed them until we get the frequency stabilized. And maybe we offer them a better electric rate for that. Most of our outages are 15 minutes or less, the few that we do have. So it's a way to surgically manage loads. So even our least significant circuit still has our state airport, our community water treatment facility on it. We don't want to drop those loads. So we're looking at load management, when we have system issues, and then we will keep marching towards dispatchable loads. It's just the battery is there now, and it's kind of the one great frequency response tool, and then we don't have to get into the complexity of trying to do that other ways. So.
The meters that you're putting in, are they got frequency measurement and able to respond to frequency? on their needs to themselves?
We have communications with them. So I will say that we installed microphaser measurement units in our grid, and we can see, I mean, they take several thousand samples a second. So our vendor's inverter on our battery system, we found by looking at the micro PMU events that they were inducing frequencies on our grid. They were inducing a 1.2 hertz frequency and a 5 hertz frequency. They didn't even know that, but again, when you throw a rock in a bathtub in a small grid, you can see every ripple. So they were actually interested in getting the data back from us, but I realized we could design those frequencies and use them for control. But we haven't got that far. Frankly, the U.S. technology is quite a ways behind Europe's in the smart grid space.
How much, this is a sort of not a technical question, but how much pressure are you under to keep the cost of electricity down in Cordova to retain the fish processing business, as opposed to, I mean, we saw lots of plants in other places, and it seems quite competitive.
Thank you. A good question. Everything we do has a direct line of savings or reliability to the customers. And a lot of what we've done is, you know, I mean, many utilities install underground power lines, but it's many of our circuits we converted to underground for a fraction of the cost that would have taken to build overhead lines. So that's a huge value savings. We've managed the way that we borrow money. I had our entire portfolio debt under 2% for almost 10 years. And so that's allowed us to keep our rates low and also increase our equity and pay a lot of our debt down. The battery energy storage system, 60,000 gallons of diesel fuel, way more than offsets the cost of the battery energy storage system. So we're extremely sensitive to cost pressures. But what we found is when we rebalanced our electric rates between rate classes, you know, we have a fairness kind of policy that we follow, that if our seafood processors are requiring us to add a bunch of infrastructure and are causing a lot of cost to utility, then they should pay their fair share. So we did our analysis that we do every few years, and they were very sharply underpaying. So our board of directors voted to increase their rates 20%. That was a lot more than I was comfortable with and staff was, but it still wasn't near what the differential. But anyway, we met, so our staff team met with each processor and explained what we were doing and why. And to a person, they said, that's okay. They said, thank you. They said, your power is so reliable, because many of these companies run plants in other Alaskan communities. It's so reliable, and it's been so long since you've had a cost increase. So we're very sensitive to it, but the high reliability is a huge advantage. It was a lot more important to them than I even realized.
And it must make it more cost effective for those fish processing places.
Absolutely. They've gotten a very highly automated as well. Even a 5-minute outage can have them down for 6 or 8 hours. They have to stop, clean all their equipment out, get their extruders, everything. They've moved a pharmaceutical grade fish oil plant from Mexico to Cordova. Another plant built a pet grade fish oil plant there. A couple of our processors said any new products, any innovation they want to do, they do it in Cordova, just because it's such a stable place for them to work. And we like that. We want to double down on that.
Could I go back to the machine or that detected the faults? You know, and the battery machine at the start.
Yeah.
It was a question actually for the electrical one. Have we got equipment like that works as cost effectively as that for detecting where faults are on the lines?
The fault finding equipment, we have very similar equipment in the UK. It's just made by a different manufacturer, but it does exactly the same thing. I read the spec sheet that you had there. And
This fault finder?
Yeah. I mean, I've worked with kit like that. I mean, that sort of kit's been available for 30 years.
Yeah. And really, we hardly ever use this. We have a much bigger, more sophisticated device. It doesn't even really need to know the cable propagation constant and stuff. It can just pinpoint where the fault is every time. I ended up using this mostly to put that low voltage pulse on that I could follow with my, with this old 70 years old now hound dog to find out where the heck the submarine cable was. Nobody knew, and then get the exact length of it so that I could do the math to find the fault. But these work really well in high impedance or low impedance faults. As a high impedance faults get really challenging, and this was kind of worthless on trying to find the fault in that cable. But
And another question I had is in Orkney, our electrical load is about 15% of our total energy usage.
mm-hmm.
So because we've got the boats and obviously vehicles and stuff like that, 85% of our total energy use is in hydrocarbons still at the moment, despite all the progress we've made.
Mm-hmm.
Do you know what the ratio is, electricity to oil, in terms of, roughly, like, so do you burn a lot more oil, even notwithstanding what you've done here with the electricity and the fish processing?
So my home energy use, and this is the cost, it's not the total BTUs or anything. I say for every $5 I spend on energy, I spend on my electric bill, driving my vehicle back and forth to work, and I live 7 miles away and usually make 1 to 2 round trips a day. 3 out of 5 heats our home, and it's 1,600 square feet, which for US is fairly small. It's well insulated, so heating cost is by far the biggest energy consumer.
And that's still oil?
The fuel oil. It's almost 100% fuel oil. There's some firewood, but not much. And then some of the people do use electricity, but they use it direct resistive heating. And that's the analogy I use. It's like you're using all the electricity up as friction. Yes, it's very efficient to convert electricity from heat, but you're converting a whole bunch of electricity to very little heat. And I've seen a lot of electric heat around Scotland. But we're starting to really, especially in Southeast Alaska where we have a lot of hydro, they're deploying the air source heat pumps, which is really just a refrigeration loop. And for every BTU of electricity, you harvest 4 BTUs of heat from the air. And so you're putting the cool air outside and the warm air into the home.
Yeah.
Except in the summer when it gets hot, then you can actually cool your home. So
yeah, we just went through a electricity price crisis, as you know.
I know.
And so our average price before that was about £2,500, and that's got up to £5,000 a year on average in a household in Orkney. And that's before we get to the heating and the oil side of it. So
yeah,
we reckon a lot of houses are spending £10,000 or more on energy in a year.
yeah, it's not dissimilar to what happens in Cordova with the fuel oil prices. And there's winners and losers. There are fishermen who do quite well, but there are also a lot in the community who are on average income, and they only have so much disposable income. And when their energy prices suddenly double, it's a big lift. So.
So how much is used electricity? How much do you charge for domestic?
So our residential rate is 28 cents a kilowatt hour, and that's our base rate. And then we pass through all of the diesel pass through. So our fuel surcharge last quarter for January, February, March of this year was 27 cents a kilowatt hour. So the fuel pass through is the same as the base electric bill, about 55 cents a kilowatt hour. Our fuel surcharge for the next 3 months is going to be like 0.003 cents a kilowatt hour, because the price of fuel has dropped a couple dollars a gallon. We over collected in the spring months because we had a lot of much higher hydro than normal this winter. I'd say it all averages out to about 30 cents a kilowatt hour once you pay the meter fee and everything associated with it. Now it's probably more like 40 cents at current fuel prices. Our industrial rate class is closer to 20 cents a kilowatt hour. And that's, the residential rate class is somewhat subsidized by the government. They have what they call a power cost equalization program. And they built a lot of hydros in other communities, and from the sales proceeds and whatnot, they use that to help offset residential rates in rural communities. So, yeah.
Have you considered looking at wind and PV as additional sources of renewable energy that will complement the the hydro that you have? You were saying that sometimes a year you can get everything you need from hydro,
Yeah,
but at other times of year you don't have enough hydro.
exactly. So it's a great question, and you know, we are a coastal rainforest, so we have tons of cloud cover. We use 75% of our diesel in the winter months. So in some ways, solar, for example, is complementary to our grid because we're a daytime peaking system and we're a summer peaking system. Normally, that would be a great fit for solar. But if you're already spilling hydropower most of that time, it doesn't help you much. Now, we're at 60 degrees north latitude, which is same as Shetlands. So at our latitude, our best solar penetration is March and April. So, and that's also when we tend to get our clear weather, and it's when we have our lowest hydro flows. Or when our weather gets clear, it gets very cold. And so we lose hydro, and solar would be, in ways, would be a good fit. But as we look at the whole picture, we would just end up spilling the solar most of the time, and where we need it most in the winter, it wouldn't help much. Unfortunately, our wind regime is really, really poor. We're a class 4 out of 7. We've worked with our tribe to install anemometers all over and tested the wind, and and we haven't even gotten into turbulence and whatnot. What's around our mountains, terrain is bad. So again, half the summer, any wind power would just be spilling and going to waste. What we really need is that bulk storage. Once we add, if we add this dam storage hydro project, now solar in particular makes a lot more sense because you use a solar during the day to save your water, and then you use the water at night, and they're very complementary. So we're looking towards solar, but if we can get there with just hydro and not have to use solar, and the pump storage gives us enough, then we'll do that. But again, looking down the road, we want to get into electric vehicles, and the more energy we can source locally in our community, the more kilowatt hours we sell, it still helps us spread our costs and keep the average cost of our kilowatt hours down. So I wandered around there a little bit, but did I answer your question?
No, you did. And I have one more question to go on to that.
Yeah.
Have you considered a preferential rate for charging of EVs at times when you're spilling hydro?
Absolutely. That's what we want to move to eventually, is having, rather than spill that excess energy. Because again, if we can power someone's air source heat pump and reduce their heating cost by 35%, that's like displacing their entire electric bill. So there's a lot more to be gained on the. It's very difficult for us to make big improvements on our kilowatt hour cost. The ways to do that is to get the diesel off and sell a lot more. But if we can make inroads into the transportation and heating costs, we don't have the technology there quite yet. One of the reasons I did the free electric vehicle charging stations, because it does provide a little bit of an incentive, and I really worked with our businesses. We put it in a place that it relieves parking congestion, but it's still close to the town core where people, can go shopping and let their car charge. But it's has a 5-year warranty and was the only wet locations charging station I find. So it's so inexpensive, it's so durable. All 4 of them have been in place for 4 years now without a failure. I just thought that's kind of a way to create a little incentive around electric vehicles very simply.
Did you say you had charging infrastructure there that had been in place for 4 years without failure?
Yeah.
Okay, so we need to get that model install it in Scotland, because ours is
to be
terrible.
quite honest, Gareth, we have had several units that have not failed in 4 years.
It's not the ones that's not.
It's not unusual. It's just some places.
Yeah.
Just this gentleman had a question earlier.
Question about the air source heat pumps.
Yeah.
Your temperature in winter time is going to be a lot lower than here. Would you be better off with ground source heat pumps?
Not so much. The new, now I haven't operated one. We just had 3 or 4 of them installed in cooperation with Pacific Northwest National Labs. They're Mitsubishi, which has the controls on them, and I wanted the controls so that we can start looking at dispatching. Maybe not outright frequency control, but we can certainly follow the availability of hydropower, and there's a lot more flexibility in when you heat your home. But the ground source heat pumps, it's very expensive to drill and dig and so forth. Now, we do have our Prince William Sound Science Center just built a new campus, and for 25 years they've been working on it, and they have a water source heat pump. So they've installed a large pumping station, and the aquarium water that they're going to pull in for their science work and everything, they will exchange the heat out of that and heat their entire facility with it. That'll be the third kind of aquarium-related facility in Alaska that does that. But mostly it's just the cost of the groundwater, and they're claiming that you can get that 4-to-1 efficiency clear down to minus 20 Fahrenheit, so maybe minus 10, minus 12. That's far colder than our climate gets. Our climate is much closer to yours than it is to, say, Anchorage, because we're right on the Pacific Ocean and we get that warm Japanese current. So our average winter temperature is like 2 Celsius. And,
we have a water source heat pump in Stromness going into the library, and it's the most efficient heat pump in the fleet that Orkney Islands Council have, and I think they have a ratio of 7-to-1 for the heat, the energy they're getting out of it. So
that's amazing.
That might be some interesting data to look at, because you've got some deep water just off here that will be quite stable in terms of.
Well, yeah. In fact, that science center is just off the picture to the left there, and that's a deep channel right there. So they're going to exchange right here. Yeah, but the energy density, heat carrying capacity of water is so much more. That doesn't surprise me. So,
yeah, I was just going to say that you've got this excess power at night when there's not much demand.
Yeah.
You may be already doing it. Is there any benefit in finding a financial incentive to get people to install battery systems in their own homes to charge at a cheap rate, and then they can draw power out of their own? Then you're not investing in those battery systems.
We thought of that, and the answer is maybe. It just it's fairly expensive. Yeah, I don't know. I'd have to think about it. The fact is, we have installed that, that grid scale battery. What I'd really like to do, and the arbitrage really doesn't happen as much as you'd think. We're peaking. I think the last I looked at the numbers about 4 years ago, we're only peaking beyond the capacity of our hydro for 200 or 300 hours a year. There are times when we're not spilling very much excess, but we do spill excess most of the summer. And that diesel use kind of all tends to happen in very compressed windows of a day or two at a time. So I think I don't think it'll get utilized enough to make it worthwhile. But what I did do is as a comparison, if the vehicle to grid, that's where I'd really like to go with it, because people are already going to have an electric vehicle, and we're getting more and more adoption. It already has the inverters on board and everything. If they would get that, I wish that technology was available 20 years ago, because instead of buying our $2 million battery energy storage system, if we truly had full robust vehicle to grid capability, we could have given away 54 electric vehicles, purchased them and given them to our customers. Yeah. If they kept a third of those plugged in and would just let us draw down 5 to 10% of their battery capacity, we would never charge them for electricity, and it would save everybody in the community on their diesel bills. Yeah. Much better value proposition, but that technology still isn't available. So they claim it is, but when you really try to put the rubber on the road, it's not there yet.
Yeah.
And the other thing is, it's energy. The simplest and best thing is just directly use it for something that helps drive our industry. We're the most rapidly growing area for aquaculture and mariculture. We have many oyster farms. The kelp farms are starting up. They're looking for ways to dry their kelp and whatnot. So doing that efficiently, everyone's talking about using heat to dry kelp, and I'm like, that's not where electricity shines. Your front-loading washer and dryer, it's the washer spinning so fast that it's spinning all the water out, using electricity as mechanical energy where it shines, so that your dryer uses very little electric heat to finish it off. So we should be looking at spinning kelp and using, we need to use energy wisely.
That's maybe a very prophetic statement to end on. So, yeah, I mean, we knew it was going to be good value, so it's absolutely fascinating, I think, Clyde, to get such an insight into, the diverse array of stuff that you're doing, and a lot of similarities, and I think people, probably looking at you with envy with some of the stuff that you've got in there. In the meeting today, actually, we were talking about how adversity creates innovation and invention in a community, and I think, when you're isolated like this, it just shows, you know, when you've got that pressure, you've got to one way out, which is your own resources. It really drives that innovation.
Could I actually add one more piece? Because we haven't touched on this at all, but it's a really important aspect of why we've been able to do what we do. So when America was becoming electrified, they had such rural areas. None of the electric companies around the city wanted to build miles and miles of power line to a farm here and a farm there. Nobody was going to pay for that. So the U.S. borrowed the U.K.'s cooperative model, your cooperative grocery stores and whatnot, and they formed electric cooperatives. So the federal government would give, like farm communities a low interest loan. Say, okay, we'll loan you money at 2%. You go buy, here's standards, just cookbook type codes and accounting and everything. They created a real simple structure to follow. And then the electric cooperatives are owned by the customers, and they elect a board of directors to make the governance decisions for the cooperative. So it's a very, very self-directed model. And like the U.S. courts won't even touch a cooperative. They say you're your own government. You the ratepayers are making your own decisions. So if you screw up, that's on you. If you do great things, it's on you. But that's allowed us as an electric cooperative owned by the customer to pretty much do whatever we want. And then because Alaska is not connected to the U.S. grid, there's no federal regulations governing us. And then even another step, our customers voted by over 80% to deregulate from the state. So instead of the state regulatory commission setting our rates, our own board of directors sets the rates. So that self-direction is one of the things that really lets us do pretty much whatever we want. And that's an important part of it, because so many environments, one company owns the transmission line, one company owns the power, one owns the distribution, and trying to get all those organizations to develop like a smart grid, good luck. But we own it all from top to bottom. So.
We ended on such an optimistic note, and then we get right into the heart of our problems again. Right. Thank you, Clay.
Thank you.
Brilliant. And I'm sure if there's people that want to come and ask questions afterwards, I'm sure Clay would be happy to do it. And although he's come from Alaska, we are in regular contact with him, so hopefully it's a relationship we can build and we can get more of these lessons going between Cordova and Orkney. So if we'd like to thank Clay, thank you very much.